Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's use triple integrals and cylindrical coordinates to find the volume of a paraboloid. While a simple formula exists for this specific shape, this example serves as a crucial demonstration of the technique, which is indispensable for finding the volume of more complex solids without the simple predefined formula. In this example, the paraboloid is defined by the Cartesian equation where z equals 8 minus into the bracket of x squared plus y squared. It is bounded by the xy plane and extends upwards. Let's take a look at the paraboloid in 3D form using a graphing tool. So this is the paraboloid, and we're going to find its volume when bounded by the xy plane. So where z equals 0. The first step in the process of finding the volume is to convert the Cartesian equation of the paraboloid into cylindrical coordinates. So we need to convert x, y and z to r, theta and z in our Cartesian equation where z equals 8 minus into the bracket of x squared plus y squared. And to do this, we're going to substitute r cos theta for x, r sin theta for y, and z will remain the same, so z will equal z. And after making the substitution, our equation becomes z equals 8 minus r squared into the bracket of cos squared theta plus sin squared theta. And using the trig substitution, where cos squared theta plus sin squared theta is equal to 1, we're left with z equals 8 minus r squared. To find the volume, we need to integrate over the region which we'll call E, and some infinitesimally small pieces of volume, shown here as dv. We need to unpack this and define our region using cylindrical coordinates. This will give us our limits of integration for r, theta and z, and then look at what dv equates to in this context. So let's begin with the limits of integration along the z-axis. The best way to think about this is that we're summing infinitesimally small pieces of volume along the z-axis between a function that defines the upper bound and one that defines the lower bound. In this case, the function at the lower bound is the xy plane where z equals 0, and the function at the upper bound is the paraboloid where z equals 8 minus r squared. So the upper limit of integration for z is where z equals 8 minus r squared, and the lower limit is where z equals 0. If you remember, when we looked at volumes using polar coordinates, we multiplied by a height component, which was the difference between the upper function and the lower function. Well, this is essentially the same thing, except we're now using an integral to do this. Moving on to the limits of integration for r, if we look down from the z-axis, we see that a circle centered at 0 is cast on the xy plane. The upper and lower limits of r will be along the radius of the circle, where we'll sum infinitesimally small pieces of volume. The upper bound of r is the radius of the circle, and is where the paraboloid interfaces with the xy plane. We therefore find r by equating our two equations z equals 0 and z equals r squared minus 8. When we do this, we get r squared minus 8 equals 0, and therefore r squared equals 8. And if we take the positive square root of both sides of the equation, we have r equals 2 multiplied by the square root of 2. The upper limit of integration is therefore the radius of the circle, where r is equal to 2 root 2. And r begins at the origin of the circle, so where r equals 0, and this forms the lower limit of integration for r. And to find the limits of integration for theta, we need to look at the coverage of r as it rotates anti-clockwise around the circle. As we can see, r goes full circle, and therefore rotates the full 2 pi or 360 degrees. So the lower limit of theta, where theta starts, is at 0, and the upper limit of integration is where theta finishes, and in this case it's 2 pi radians. So we've defined our region using the limits of integration. Let's now unpack what we are integrating. So in our case it's dV. So dV represents infinitesimally small pieces of volume. We're using triple integrals to sum each of these to get the total volume. Let's look at the dimensions of one of these. If we look at the green shaded region, this represents an infinitesimally small piece of volume dV. We can think of this as a tiny rectangular box where the volume is given by the height multiplied by the width multiplied by the length. So let's apply this to the green shaded region. We can see that the height is along the z-axis, and it's an infinitesimally small piece of z represented by dz. The width of the box lies along the radial distance r and is an infinitesimally small piece of r represented by dr. And the length lies along the arc of the circle and is infinitesimally small. Now the arc length of a circle is given by the radius multiplied by the central angle theta. In this case, theta is infinitesimally small, represented by d theta. If we now put all these infinitesimally small dimensions together, we see that the volume dV is given by dz rdr d theta. And we sum all these pieces of volume using our triple integrals to get the total volume. So now we have our triple integral where we're integrating dz rdr d theta. So let's begin the evaluation process, beginning with the inner integral. And so for the inner integral, we want to integrate from z equals 0 to z equals 8 minus r squared dz. And using the power rule, this integral evaluates to z. And plugging in the limits of integration, we have 8 minus r squared minus 0. And this equates to 8 minus r squared. For the middle integral, we want to integrate from r equals 0 to r equals 2 root 2, 8r minus r cubed dr. And using the power rule, this integral evaluates to 4r squared minus r to the power of 4 divided by 4. And plugging in the limits of integration, we have 32 minus 64 divided by 4 minus 0. And this equates to 16. And for our outer integral, we want to integrate from theta equals 0 to theta equals 2 pi of 16 d theta. Using the power rule, this evaluates to 16 theta. And plugging in the limits of integration, we have 32 pi minus 0. And this equates to 32 pi, which is the volume of our paraboloid.